We have finished talking about work. We'd like to move on and talk about power now. Power is just the rate at which you can do work. So the equation for power is very simply work over time. It's a nice, easy saying, work over time. That's the equation for power. There's other ways than we can write this because we know other equations for work. Work is force times displacement. If you take force times displacement over time, that's another way that you could write power. And if you notice displacement over time, we know what that is. That's velocity. So another way you could write it is force times the average velocity. That'd be another way to figure out an equation for power. We always joke around about the question, what are the units for power? And the answer, of course, is exactly, because the units for power are in watts. Watts. What is a watt in kgm per s? Well, we have force times distance over time. So force is newtons, and that's kilogram times acceleration, kilogram meters per second squared. That's a newton. We have a time on the bottom, so that'd be another second unit. And on the top we have another displacement unit, so that'd be meters. So we have kg m squared over s cubed. There's the MKS units. Instead of using those units, of course, we call it a watt. A watt of power. A lot of times we might divide this by 1,000 and put it into kilowatts. You might have heard that before when we talk about paying your power bill or your energy bill. We'll talk about that some other time. There's another unit that we used to use instead of watts because our source of power in the olden days, of course, was the horse. So the average horse could do about 750 watts of power. So we have a conversion factor of 1 horsepower equals 750 watts. It's actually a little less, like 746 or something, but we're just going to average it out or round it off. 1 horsepower is 750 watts. So you'll be able to use that to convert power units from horsepower or watts, whichever you need it in. Okay, so let's do a problem here that involves power. If you remember these equations here. Let's go on the next page. A car is driven up a parking ramp 12 meters high at a constant velocity in 20 seconds. The mass of the car is 1.5 metric tons. Calculate the power output of the car's engine during this time in horsepower. Okay, so power equals work over time. We know that that's the force times the displacement over time. And in this example, we have it doesn't really matter about all the driving up the parking ramp. The matter is the displacement is 12 meters high up. So the force that would take to raise this car up would be the weight of the actual car, which would be m times g. The displacement that we're going to move it up is, we could also say, is the height, which is going to be 12 meters, and we're going to divide that by the time. So what's the mass of this car? Well, it says 1.5 metric tons. You might not be aware of what a metric ton is, but a 1 metric ton, most of you know that 1 ton is 2,000 pounds, but a metric ton is 1,000 kilograms. We call it a metric ton because it's actually like 2,200 pounds, so it's a little bigger than 2,000 pounds. So a metric ton is a little bigger than, about 200 pounds bigger than a regular ton. So anyway, it's 1,000 kilograms. So anyway, this says 1.5 metric tons. So that the mass then would be 1,500 kilograms, and then gravity is 9.81. The height that the car is going to be lifted is 12 meters high, and the time that it takes to do it is 20 seconds. Now this will give us our power in watts according to this formula. But we didn't want it in watts. We actually want it in horsepower, which means we're going to have to also divide by 750. There's 750 watts in 1 horsepower. And if we do that, then if you do this calculation, hopefully you've kind of paused the movie and tried to do this problem on your own, see what you come up with. We get around 11.8 horsepower was the power output of this car. Okay, hopefully that makes a little sense. Really, we can talk about power of a rotating object also. If power equals force times displacement over time, then we can put this into rotational world also. The force in rotational world corresponds to torque, and displacement in rotational world would be angular displacement. That'd be theta. Of course, time is still the same thing. So that would be an equation we could use for power and the power of a rotating object. Now, angular displacement over time is angular velocity, so we could have torque times the omega sign. Would also be rotational power. And torque, of course, is the force times the tangential force times the radius of the thing that you're turning times angular velocity. And angular velocity would of course have to be in the radians per second units. I don't have a problem for us to practice on this, but this is just like any of the other equations. We can put it into rotational world with rotational equation and still be able to do it just like we'd do it normally. So that's a quick overview of power.